something my grandfather used to say fairly often, and that is when something can't go on forever, it won't. And I think that's the reality. That quite simply is the reality that we're facing, not just with energy, but with the next topic, which is water. And Anne-Marie Boulay will come to speak with us, and let me give her a bit of introduction. You're here somewhere. I saw you earlier. And she graduated from chemical engineering at McGill University in 2006, and during her studies, she completed a minor in environmental engineering, and at that time at Montpellier in France, and a 16-month internship with the Environmental Department of General Motors of Canada. She brings a great diversity of experiences with her. After graduation, she spent the first 6 months in Peru teaching entrepreneurship to women, and then worked as a consultant in environmental management in Montreal before joining CIRAIG, which she'll tell us about perhaps, team at École Polytech in Montreal, completed her PhD in life cycle assessment and water footprint. She's the Canadian delegate for the International Standards Organization on water footprint standards and building an international consensus on methodology, and leading the WLCA group and life cycle initiative. So would you please come and speak with us?
Good morning. Thank you for the introduction. To make this simple and compare it to the previous speakers, I'm not an agricultural engineer. I'm also not an animal scientist, but I am a chemical engineer who diverted towards environmental engineering, specifically life cycle assessment and water footprinting, because as an engineer whose main concern is sustainability, I found these tools to be essential to guide our decision making towards our sustainability path. And I hope that this presentation will convince you of the same thing. So let me see. There you go. So when we start talking about water, first question to ask ourselves would be how much do we actually have to see how much we can use. And precipitation on land amounts to 119,000 cubic kilometer per year. And if this represents 100% of what we get, then it is separated into 62%, which will go back to the atmosphere right away through evaporation and transpiration. And the remaining balance will become runoff, out of which human will take water for their uses, agricultural, domestic uses, and industrial, which in total only amounts to about 3% of all available water. So we can wonder then, why do we keep talking about this as a problem? Well, the World Water Council put it very nicely by saying that there is a water crisis today, but the crisis is not about having too little water to satisfy our needs. It's a crisis of managing water so badly that billions of people and the environment suffer badly, which means that 3,900 children die every day from waterborne diseases. 1 out of 6 people lack access to safe drinking water. 8, what we call mighty rivers, are running dry from overuse, which greatly affects humans and ecosystems, which means that water is actually not equally distributed in time and space, and that its quality is degrading around the globe. To show you a little bit with maps, I mean, you've seen many scarcity maps, I'm sure. We can see here in blue region for the first map, the area where water quantity is more of a problem. But we're in Canada, and here we're not so concerned with water quantity, at least not in this part. But we do have also quality issues. And the darker regions, darker red and orange regions on the bottom map, shows that some regions also have quality problems. So then how do we tackle this? As you might know, Kelvin, he said if you cannot measure it, you cannot improve it. So we need good methodologies to be able to measure the impacts that we are causing on water in order to protect this resource better and work towards improving the protection of it. So I will present you with the life cycle approach. I'm assuming some of you might have heard about it. And if not, this is a short introduction. Life cycle approach is a methodology that can be applied to any product or services. Here's a car, but it could be an agricultural product, it could be a steak, it could be a box of cereal. And basically, for any products that we consume, we have to look at the entire life cycle of this product. This means the extraction of raw material, the production process, the transport, packaging also, product use, and then disposal of the product. And through all of these stages, energy and resources are taken from the planet, and emissions and waste are put back into the environment. And all of this can generate impacts onto the environment. So the first thing we do when we do a life cycle assessment is that we take the list of all these emissions and waste and energy and resources, and then we end up with this long list of thousands of different substances. And then we can, in an ideal world, compare this with a different scenario and see which one has been better. For example, if we talk about an electric car, we can first think that it has zero emissions, so it must be better for the environment, but we have to consider the entire life cycle, because what if you're actually just burning coal somewhere else? It may seem better, but if you don't look at the big picture, you might simply be displacing a problem either in time, in space, or from one impact category to another. So then how do we truly compare two different scenarios? Comparing a list of thousands of substances is not really manageable. So then we use mathematical models to translate these emissions and substances into specific problem categories, about 10 to 12, which will touch eutrophication, acidification, toxicity, global warming, and then it becomes a more manageable amount of numbers to compare and to assess. But if you want to further reduce this amount of numbers and have more meaningful impacts, you can go further into the modeling, and then you will end up in results depicting the impacts on 3 areas of protection: human health, ecosystem quality, and resource depletions. And then comparing two scenarios become hopefully easier, and one will perhaps be obviously better than the other. So this methodology is really a tool for decision making, which quantifies the potential environmental impacts. We, of course, never pretend to actually measure real impacts, but it's a potential impact over the entire life cycle of a product. And there's a series of ISO standards, 14040, 44, which really frames this methodology. But I'm here to talk to you about water and not simply life cycle assessment. So we have water availability as one problem category, and let's see how this is taken into account and how this has moved towards water footprinting. So having the same framework and looking just at the problematic of water, we have the inventory, which will list all the water withdrawals, water releases, but also all the emissions that can affect water, directly or indirectly. And this will lead to 2 categories of problems. We have water quality problems through pollution with toxicity, eutrophication, acidification, for example, and we have resource availability problems, which will themselves lead to specific damages to human health, to ecosystem quality, or to resource depletion. Now we talk of a water footprint. You've for sure heard the word carbon footprint. Well, water footprint is a similar concept that we apply to water, which quantifies the entire problems that will affect water. So if we stay at the problem level, it will be both the pollution and the resource availability issues. Or you can do the same thing at the damage level, accumulating all the impacts on the areas of protection. This is really just a matter of choice. Usually the US prefers to stay at the problem level. Europe is more towards damage. It's a question of preferences. But now let's look into which metrics do we have in order to actually quantify these potential impacts. So historically, there was the Water Footprint Network, which is based in the Netherlands, which were really the pioneers and came up with the word water footprint and proposed this volumetric methodology. They quantified blue water, which is surface or groundwater that is being used in order to produce a product. Green water, which is all the rainwater embedded into the product, typically for agricultural produce. And gray water, which is a hypothetical dilution volume to dilute pollutions. So this was really great first steps, but then methodologies have kept evolving in parallel organization, and specifically the ISO organization has just came up, so this is a very hot and new news, with the ISO 14046 standard water footprint principles, requirements, and guidelines. This was a 5-year process which included, just like ISO's processes, people from all over the world, all types of stakeholders in the fields. And for 5 years, we discussed and came to a consensus. And this was just approved in May 2014. It's now currently being edited and translated, and you can find it online in the next few weeks. This standard, to run you briefly to the content, says that water footprint should be life cycle based and not focus only on one part of the life cycle. And you can do a life cycle analysis completely, which includes a water footprint, or you can do it as a standalone water footprint assessment, disregarding other categories. The third point, which is very important, is that the results should include impact assessment, and you cannot simply compare two options with volumes of water, because 1 meter cube of water being consumed in Canada, in Egypt, in South Africa will not have the same impact, nor will it cause the same problems on the ecosystems or for humans. A water footprint should include a comprehensive impact assessment, which means all impacts related to water. Even if you may not be consuming water, you can still be degrading it. And you may end up with one or several indicators. And I want to say also, this is a standard that, of course, like ISO standards, if you're familiar, if you read the entire standard, you still don't necessarily know how to do a water footprint. Just to reassure you, there's this guidance document that will also come about maybe 6 months to 1 year later, 14073, which will be a series of examples of applications, which will really be more concrete on how to do this. So this entire framework basically can lead to different types of water footprint. You can have very specific ones, which you need to qualify. So you can do a water scarcity footprint, water availability footprint. You could do a water degradation footprint. So you only look at a subset of indicators. However, if you want to perform a real comprehensive water footprint, then you would need to look at both water availability and water degradation impacts. Similarly, also at the damage level, we also call this midpoint and endpoint. You can look at only availability, only degradation. You can also look transversely and saying you want to perform a human health water footprint or an ecosystem water footprint. But again, to do a comprehensive water footprint, you need to look at all aspects. So another way to show these different metrics, I really like the Russian dolls analogy, because this is really how we go from a very simple assessment where you only look at water scarcity in a region, and then you have a water scarcity footprint. And this assesses the impact from a reduced water availability from having consumed water. Or you can go one level higher, include a little bit more impact, and here you look at the reduced water availability from consumption and degradation. This means that just by degrading water, you can also reduce its availability for other users who can no longer use it because it's so polluted. If you want to go even higher in your assessment, then you would look at all the degradation impact and all the availability impact, and this would be a complete water footprint, which is in itself one component of a complete life cycle assessment, which would then consist of a carbon footprint, a water footprint, and other types of footprint, which would include all the remaining impacts. So if I show you a little bit what can we do with a water footprint results and how it looks like, we have here an example of a water footprint from a load of laundry. This was done in collaboration with Unilever for a specific product of theirs where the suppliers are located in various European countries as well as India. And then the manufacturing of the product is done in Spain. The laundry is performed in France, where you have energy input, mainly nuclear, in France, water, and then the clothes are just hang to dry. And then you have an end-of-life release into the environment through a wastewater treatment plant, and then in 20% of the cases directly to the river. So I chose to show you just a selected amount of results. Here this will be the equivalent of an ecosystem water footprint. And all these units are the same units, so potentially disappeared fraction of species, which means that you could add all of them together. And there's two types of information you can draw from this. First, you can look at in terms of impacts to the water resource, where does it come from the most on the ecosystem? So you can see that having consumed water will have an effect on terrestrial species, and then water degradation impacts will be linked to ecotoxicity and to eutrophication. You can also see which stages of the life cycle of your product will have the most impact. In this case, for ecotoxicity, the release of some of the contaminants in the environment will have an ecotoxicity impact. And also, the use of energy will have a eutrophication potential. And then you can think of solution like producing a cold water detergent, which will allow you to wash in cold water, and this will actually be easily quantifiable on your resulting reduction in water footprint. Other uses for this is communication and labeling. There's many initiatives right now, especially in Europe, going forward towards labeling of carbon footprinting, water footprinting, or product environmental footprint. And companies that are really at the forefront are engaging this already and communicating on their websites on their impacts related to water and carbon and etc. For this, we need consensual and standardized methodologies. As I've shown you, we have a standard that will give you the guideline and the principle, but we're still working on one consensual and standardized methodology so that we can compare the results of all these footprints. And this is why I'm just going to shortly present to you the working group WULCA. WULCA stands for Water Use in LCA, and it's a sub-working group of the UNEP-CTAC Life Cycle Initiative. UNEP, United Nations Environmental Programme, CTAC, Society for Ecotoxicology and Chemistry, and Life Cycle Initiative is the joint group where life cycle assessment, application, and development is really hosted. And this working group was founded in 2007, and it now includes about 100 experts from 21 countries around the world. And it really fostered the development of the methodologies to assess impacts from water use in LCA. The first phase was to set up the framework on how to evaluate these impacts. This was actually done here in Montreal by an ex-colleague of mine. And then the second phase was to look at all the methods that emerged from this framework to say, okay, how do we compare these? How are they different? What is the difference in scope? And what are we missing in terms of methodologies? And then the last phase was a quantitative comparison, where we really analyzed the methodologies and said, okay, this modeling choices will affect the results by so much. I've shown you one scarcity map, but I'm sure you've seen many, and they all look slightly different because there's many different ways of looking at scarcity. And it really depends on which question you're ultimately trying to answer. If you're trying to answer what are the impacts on the environment of using water, it's not the same thing as trying to answer what are the impacts on human health, or what is the risk to my business to go in this region, and all these questions may need different indicators. So all of this to lead us now to the current mandate that we have, which is to guide the scientific development of a consensual and operational method, which shall be in line with the ISO water footprint standard as well as the LCA principle. And we have until 2015 to do this. We're already well on the way. So I'm the project manager for this, and my colleague here, Stefan Pfister in Switzerland, is the deputy manager. Please feel free to contact us. You can go on the website. There's many relevant publications on the topic of what I explained, going even a bit further. There's an update on our activities, on the trainings that we give. You can join also the LinkedIn group where we have the main announcement being posted there. And that's it. On this, I'd like to thank the sponsors who really are funding this project until 2015. And don't hesitate to contact me if you have any further questions.